Okay, well, welcome to the Sums of Fractions Part 2. So today we are going to just continue to work on this idea of how it is that we add, right? Sums, how we add our fractions. So let's dive in and start playing around. Let's see here. Let's go ahead and take 2, 6. We're going to add this to, how about 5, 6? Let's do that. Let's do that. Okay, so here's a couple of things. We've kind of already explored two things that are going on. One, I have this great option of being able to model this and then put together my pieces. And then we have also noticed a trend mathematically how I can solve this. So let's go ahead and model first. So again, if we're going to add two fractions together, it'd be really helpful to see those two fractions. And as you can see, both of which are cut into, I guess would be our best, or divided into 6 pieces equally. That's what that denominator means. That means we've taken our model and we've cut it into 6 equal parts, right? So we'll do that with both. And our first fraction says 2 out of 6, so we got to shade in 2. And our second fraction says 5 out of 6, so let's shade in 5. And if we were to put these together on one model, let's rephrase that model there. If we were to put these together on one model, we still have 6, right? Because that's the size of the pieces. And that didn't change. The size of these pieces didn't change. And we have 1, 2, 3, 4, 5, 6 of them. No. Oh, wait, I didn't shade in 5 over here. I only shaded in 4. Okay, 7 of them. I was like, man, that didn't work. We have 7 of them, so let's shade that in. We have 1, 2, 3, 4, 5, 6. But I need 7, so we got to give ourselves another model. Same size pieces, and shade in here. So what we see that we have here is we still have 6s, and I have 7 of them. So we have 7, 6, and that's what that is, right? This is still cut into 6 or 7, 6. So this would be like 7, 6. Or if we really looked at what this is in this model in general, what these numbers really state, well, this is one whole. And then what's left over is the 1, 6. So 7, 7, 6, or 1 and 1, 6 are both acceptable answers. So that's like modeling our addition, right? Like that's how we model this addition. But if we looked at like what's happening, what's the trend is, again, look, our denominator never changed. So really we just slide that over, and then we added our pieces. We added our numerator, which is 2 plus 5 is 7. And as you can see here, if I do it mathematically, I get the same thing. 2 plus 5 gets me 7. The 6 stays the same. And again, that what that states is I have, if we can see in the model, I have one whole and then 1, 6 left over. Right? So again, both these answers are acceptable. We'll learn how to do all that. So let's keep going with that. Let's play around with another one. Let's take 7 tenths and add that to 1 tenth, right? Okay, well, let's look at the mathematical trend now. What we notice is that when our denominators are the same and they stay the same, so that's a 10, and then we're just adding our numerator, which is 7 plus 1, that's 8. So I should have 8 tenths, right? That's mathematically. I just slide over that denominator, add my numerator, boom, I'm done. And of course, to make sure we know that this is working for sure, let's just do the quick model of these two to make sure we get the exact same answer. So this is tenths, so 1, 2, 3, 4. 1, 2, 3, 4. And this is 7 of them, so 1, 2, 3, 4, 5, 6, 7 tenths, and this is 1 tenth. Okay, so let's put these together on one model. Oof. And we see, if we were to count these, we have 1, 2, 3, 4, 5, 6, 7, 8. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8. And there you go. That's 8 out of 10, which is the same thing. So now we can start to see we have these trends. We can use this modeling, or we can just use this trick we're learning about addition here, right? 6/12 plus 7/12. Okay, well, mathematically, my denominator is the same, so it stays the same. And then if I just add my numerators, 6 plus 7, I would have 13/12. Okay, does that check out? Does that check out? Okay, and again, this is top heavy. We're gonna learn how to really write our final answer. This is kind of the answer, it's not the full answer, right? There's an equivalent way to write this more correctly, but let's just check this out through modeling. So, let's see, I don't know, I just felt like changing up the way my models look. So that model plus that model is gonna equal this model. So we need 12 pieces. So 1, 2, 3, 4, 5. There's 12. 1, 2, 3, 4, 5. There's 12. 1, 2, 3, 4, 5. There's 12. This is 6 out of 12. And this one is 7 out of 12. This is 6. Here's 7. 2, 3, 4, 5, 6, 7. So if I counted all those up, right, I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 12s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're going to need another model. 1, 2, 3. And so that was 12, 13. So this would be our answer as a model, which is 13/12s, or we can see in this model here, this is one whole because we did all of it. So I have one whole and 1 out of 12 left. Again, this is the answer we really want to learn how to do. But for now, if you're still kind of in this form, that's fine. It's going to work, okay? All right, let's just keep going with this because now we're starting to see there's this mathematical way and then there's this modeling way, right? There's an algorithm, I guess, is probably the best way to put that. We can solve things using an algorithm as opposed to always modeling, okay? So, all right, this time there's three fractions. I got to add them together, no big deal, right? Because the rules don't change. What we've noticed so far is that with my denominator being the same, it's all my pieces will be the same size. So they're always gonna be force, according to the denominator. It will always be force. Okay, and now let's just take our numerators and add them together. And that will get us our answer. So 3 plus 5 is 8. 8 plus 1 more is 9. That's 9 force. Okay, all right, so just to prove that this works, let's model it again just to see. So this time I need 3 models. Okay, I'm gonna add these together. They're all force. So this is 1, 2, 3 of them. This is 5 force up here. Let's see, that's 1, 2, 3, 4. I guess I need one more. 5. And this is 1 right here. Okay, so if we counted up all the force that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now we got to put all that together. Let's see here. So I have 9 force. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this answer is interesting because if you look at this, look at here. This is 1 whole, and this is 1 whole, and then this is 1/4. So that'd be 1 plus 1 plus 1/4. So 9 fourths is the same thing as 2 and 1/4. Like these are equivalent. And there we go. It works, right? It works. The model works. The algorithm works. The model works and the algorithm works. So why not just do one more? Let's do 5. You know what? Actually, let's do this. Let's say, well, we now have faith in our algorithm. So let's go to something like that. Maybe like, what if we had something that was just much larger, right? Like, how am I going to model this? How do I model 50? I mean, I could sit here and cut my thing into 50 pieces. I really could. Or I could have faith in the algorithm and say, okay, well, the denominators are the same, so that won't change, right? I'm cutting it into 50 pieces no matter what. And then let's just look at our numerators here, we have 31 plus 17. I have 31 pieces over here plus 17 pieces over here. So altogether, I get 48 pieces. So that's my new numerator. And there it is. I have 48 50ths, which still is less than 1, right? That's still less than 1, because remember, the denominator says I took one piece, I took one, and I cut it into 50 pieces. So I have a lot of little pieces. Let's see here. How could we do this? We go 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10. And then we have 1, 2, 3, 4, right? So yeah, they're all not exactly the same. It's kind of funky over here. I get that. But this is my whole, and it's cut into 50 pieces, and I have 48 of them, which means I have all of the pieces shaded in except for 2. Should have shaded that a different color. All of these are shaded in here, except for these 2 over here, this one and this one. Let's highlight those with a different color. These 2 were not shaded in, right? Because this over here, this is 48 of them, right? 48 of them. 48 in here, and there's 2 left over. So I'm still not even at a whole, even though this is a big number, 48 out of 50. That's still less than 1, because we took 1 and cut it into 50. Okay, so anyway, just want to talk about that as a side note. But again, here we go. Here's that. So let's just do one more practicing with the algorithm. Let's have faith in the algorithm. What if we had 13 20ths and we were adding that to 2 20ths, and then we had to add that to 6 20ths? Okay, well, again, the algorithm is stated my denominators are the same, so the size of my pieces will not change. So we're going to put all that over. There's 20 right there. And then let's just add what we have up top. Let's add our numerators. We have 13 plus 2, that's 15. And then we have 15 plus 6 more. What is that? 21. So we have 21 out of 20. 21 out of 20, which now that means I have 1 and 1/20th as well. Both of these answers are okay. As you can see, 20 out of 20 would make a whole, and then have 1 left over. So that's really this idea of the addition of fractions, is like, if my denominator is the same, there's a cool trick we've just learned, and I want to encourage that you try that out, but I also want to encourage that you make sure that you model too. Like, do both of them. Do both of them so that you can compare and make sure that you're getting the same answer. And once you're comfortable, then move on, right? But as always, I want to appreciate your hard work and everything that you're doing. Keep it up, and we'll see you really soon.